Please get admitted quickly. You are coming late. 6 people are still waiting there. Let me find them, admit them all. People are still joining till the end. So let me start lecture. Bismillahirrahmanirrahim. So I was discussing in previous lecture this transfer heat gain. You know, this is very important formula of heat transfer, and the requirement of this subject is to get through this chapter 2, where all these things are mentioned in detail, and again do the chapter 2 problems. Q is equal to U A T2 minus T1. This is a very famous equation of heat transfer. Heat transfer calculated by this formula is called as transfer load. So U is reciprocal of all thermal resistances, sigma RTH. How to calculate sigma RTH? There is a short example in the book, and there is a data given in the table 4.4 at page 68 of the textbook. And RTH means total thermal resistance of wall, a roof, slab, or any construction material. That's units of meter square Kelvin per watt. You as a mechanical engineer should know this. And these things are usually asked in interviews and quizzes and maybe in presentation when you present any project with this formula. So A is the area, T, O is the outdoor air temperature, Ti is indoor air temperature. In case of transfer load, you should know the structure of the building like this. This is a wall structure shown here in this example. Heating and cooling load calculation example. It is the figure 4.3 of your textbook, example 4.3. So here you can see that this is outside air is this side, inside air is this side. And as you can see in this figure, try to see the waiting room, sorry. These latecomers are disturbing. The time will come and I'll refuse to admit anyone. Now you can see clearly this diagram. This is a diagram of a wall. Wall structure should be mentioned. This outer layer of this wall is made of which material? You should know this is face brick. Its thickness 90 millimeter. Next is a air space. There is a gap between after this wall, and there is another wall of sheathing, some sort of sheet there, and it is 13 millimeter fiber board. It's a fiber board sheet, and it is 13 millimeter thick. Now you know the material and thickness of this component. Now here this component with a zigzag spiral wave like this. So this is made up of mineral fiber. This insulation material called mineral fiber, and its thickness should be known. Here it is 75 millimeter in this example. So after this sheathing board and after this insulation board, we have another air space. So before and after this insulation, there is air space. Remember, air is a very good insulator. Air space acts as an insulator. So its air space is given, and there is another surface. It is made of a board, gypsum board, and gypsum board shows good finish from inside, and it has 13 millimeter thickness. So every component of material should be mentioned, its material should be mentioned, and thickness should be mentioned. But you see inside air and outside air. Inside wall is in contact with a film of air. Outside wall is in contact of a film of air. This film of air also acts as insulation. So this all has its resistance. So these thermal resistances should be taken from property tables. This is given here in this table. This is the sold example. So from the table 4.4, you can find outside air film resistance is equal to 0.029 meter square Kelvin per watt. See the unit. Reciprocal of this unit is the conductance. So resistance and conductance are opposite to each other, reciprocal to each other. That's why units are also reciprocal. Units of conductance is watt per meter square per Kelvin, and unit of thermal resistance is meter square Kelvin per watt. Now, face break of 90 millimeter you can find from the table. Its value is written here 0.68. Air space value 0.170. Sheathing fiber board 13 millimeter 0.232. Insulation 75 mm fiber glass 1.94. And air space again 0.170. Gypsum board 13 mm 0.080. Similarly, inside air film has 0.12. So you can see air space, air film outside has different value than inside. Inside air resistance is more than outside, because outside air is turbulent and its layer is broken, so it causes less resistance to thermal heat transfer. Now, we will algebraic sum of all this is 2.821 meter square Kelvin. Reciprocal of all this is called R total. Reciprocal of R total is called conductance, and that is U, overall heat transfer coefficient. This will go to this formula. Q is equal to UA/TO minus TI, and you will know the result. Heat transfer through transfer heat because of temperature difference to this wall. So now, next page. This page shows estimation formula for transfer of heat gain through floor slab. Remember, through floor slab, usually in our atmosphere conditions in summer is not required. It is required in winter in cold countries because a lot of heat transfer takes place to the earth. Heat loss takes place through the earth from inside air. Inside air is hot in winter, and outside surface temperature and depth temperature in 3 meter depth temperature of ground is very low, and because of that temperature heat transfer takes place because of this temperature difference, and there is no exact scientific formula for it. There is an empirical formula or based on experience formula, which is Q slab is F multiplied by P multiplied by T O minus Ti, where F is a constant watts per meter Kelvin, and it is given in the textbook. F is equal to 1.4 for uninsulated edges. You know, edges of the floor between skirting and floor are insulated at the time of constructing floor. So that with fiber board or something like that. So if it is insulated, then this factor is 1.4. And if edges are not insulated, edges of the floor are not insulated, there's no insulation between floor slab and the walls, then this factor will be 0.9. So by multiplying this factor F multiplied by perimeter, perimeter is the linear length of the all sides of the room. Now multiplied by delta T, TO minus TI. TO is the atmospheric temperature, outside air temperature, design temperature, and TI. Remember, this is for winter only. It is written in the heading also. In summer, you don't try to calculate it, there is no need. Because temperature of the floor, ground under the floor is same as temperature of the floor inside. So there is no heat transfer in our climate. In cold climate, it is done. Now, I'll take another file. Now I'll show you data available. You see, in this lecture, I cannot cover all of the topic of heating load, cooling heating load calculation. This is half of it. It will be completed in third lecture. Two lectures are, this is second lecture, third lecture will be inshallah tomorrow at 9:40. But here, today, I will cover this much which is shown here. You know, these property tables are very, very important for calculation of heating cooling load. So this is cooling load factor for lighting. We have discussed this topic, CLF. For CLF, go to this table. Here it shows number of hours after lights are turned on. Because CLF is a measure of how much it takes to transfer radiation load to the machine. And these hours should be known when lights were turned on, when AC was turned on before, during the cooling process. And now fixture, X type fixture, Y type, two types of fixtures are mentioned. So this description given here in the footnote. So according to this fixture type X, it is a recessed. Fixtures are of different type fixture. Architects know it, and you as a mechanical engineer should work in close liaison with architects, civil engineers. And fixture description is X is recessed type lights which are not vented. So lights are closed in a box. Box is closed in the ceiling, and box has perforated holes in it. So this is called with ventilation. So without perforated holes, not ventilated. Now the supply and return air registers are below the ceiling. Supply and return air registers are below the ceiling or through the ceiling space and grill. You know, these lights are fixed in supply air also near about, or is part of that grills which supply cold air. So Y type are vented are free hanging lights. They are just free hanging lights. They are not part of any cooling device like a register or that diffuser. And the supply air registers are below or through the ceiling, with the return air register around the fixtures and through the ceiling space. So sometimes registers are down the ceiling, down the supply, down the ceiling. That is, we are talking about false ceiling. And lights are in the fixed in the false ceiling, hanging in the real ceiling above. And return air goes through. Return air sucked by the return air duct through the ceiling space. So in this way, it is ventilated. There are holes inside the light body, light casing, and cold air circulated through this. So according to this time, here is number of hours of operation, 10 hours, 16 hours, 10 hours, 16 hours, two different columns. For 10-hour operation in one shift, for 16-hour operation, two shifts. So, and this is number of hours after lights are turned on, hours of operation. So by using this table, we can find out the CLF, cooling load factor. That means what is the effect of radiation transfer from these lights. Now, heat gains from occupants. Another table, table 4.7 is from the textbook. For your convenience, I have copied it here. Don't need to go to textbook. Just get it printed. Hard copy, keep hard copy of all tables and property charts with you to be able to calculate to solve the problems, numerical problems. You can see it depends on activity of the person, how much heat he will emit to the air-conditioned space. Heat gains are given sensible heat gain percentage. Here is total heat gain, and here is sensible heat gain percentage. In some text, in some handbooks, this may be given only sensible heat and total heat. So you can calculate by deducting from total heat, sensible heat, and you will know the latent heat. So we need both type of heats from the persons, that is latent and sensible both. From these two columns, you can calculate how much will be latent heat. Sensible is 0.75 of this 70. Here, sensible is 0.6 of 100. Here sensible heat load is 0.5 of 150. So these are total heat. This column shows total heat. This column shows percentage of sensible heat of the total. So you know the sensible heat, you know the now latent heat. And here is the activity: a sleeping person, seated, quiet person, standing person, walking person with 3 kilometers per hour. It may be a gymnasium, and somebody may be some may be doing exercise on treadmill. So now office work and sitting on chair and table and working is while sitting on the table working also emits 150 watt energy. Human brain works. Human brain works. Thinking power generates 150 watt energy. Now teacher stands, walks, and speaks. So these all activity consume his body energy, and this body energy is emitted in the form of heat. So that is 175 watt. So remember, when Dr. Shakur is standing in the class and delivering a lecture, so he is equal to his emission of heat, total heat is equal to 175 watt of a bulb. So now retail shops, in retail shops, people are sitting, walking, working, eating, things like that. So that is 185, their activity. What about industrial worker? Industrial worker, मजदूर की औकात हमेशा मुश्किल होती है, वो फिजिकल एफर्ट करता है, मेंटल एफर्ट नहीं करता. तो फिजिकल स्ट्रेंथ की वजह से वो फिजिकली स्ट्रांग है और he perform physical activity like lifting the weights, like hammering the iron and working in front of hard things, and like lifting the weight, bags or luggage or cargo, things like that, and walking and moving and operating a machine with physical effort. So such a person, industrial worker, has 300. It may have 300 to 600 watt load. Depends on his activity. Now in table 4.8, space per occupant. Sometimes number of occupants is not known, and mechanical engineer should not wait for other. Remember, this word is very, very selfish. When you work in an air conditioning, in a consulting firm where it will be one mechanical engineer, one civil, that is you, one electrical engineer, and one civil engineer. So you should have data from electrical and civil engineer to be able to calculate these loads. But they may not assist you. They may refuse. They say, "I'm not started my work. It's not your business." So in that case, you have to choose this table and go assume your own occupants. So number of occupants you can assume by yourself. According to, if it is residence, you can assume that there are 2 to 6 persons, and if it is office, so this is according to this is not for resident 2 to 6 occupants, not floor area based. But for office, you calculate with the help of floor area of the room. The floor area is 10 to 15 meters square. So you assume that for 10 to 15 meters square, there will be one occupant in office building. 10 to 15 meters square for one occupant. If there is a big room and there are more than one officer sitting there, so every officer will take 10 to 15 meters square area. So that's why total floor area of that building you can divide by 10 or 15, and you will get number of persons sitting inside. If it is a retail shop, mega store, thing like that, people are walking with trolleys and along the shelves and picking the things and leaving again. So going to the counter, coming from the counter, going to the shelf. So now 3 to 5 meters square per occupant you can assume. Total floor area of the shop should be divided into 3 or 5, and you will get number of persons inside the shopping mall. Now a school, of course, you don't know how many students are registered, how many students are present today or the day when you are calculating. It is not required. You should know the total area of classrooms divided by 2.5. You will know number of students. So you have to assume this number of students. Students may be less, students may be more, but this is standard 2.5 meters square per occupant. Auditorium may be fully occupied, may be half occupied, may be empty, but for load calculation, you have to calculate 1 meter square per person. For example, there is a mosque. How you should know? Cooling load because of occupants, because of people. In Jummah prayers, mosque will be full, and you can assume 1 meter square per occupant. You assume that mosque is full. All musallas are full, and total area, knowing the total area of the mosque, covered area of the mosque, divided by in meter square, the same will be number of meter square of the floor area will be same will be equal to the number of occupants, number of namazis in there. Now, this table, sensible heat cooling load factor, also you will need, it depends on total number of hours in the space 2, 4, 6, 8, 16, and this factor will be multiplied with the number of occupants formula. Now, let us take another share. Now, transfer load data, chapter 2 data is available. Chapter 2, I have asked you to do solve problem. You've already done it, but I've again repeated here all formulas from chapter 2. This is heat mass transfer and fluid mechanics formulas. So without this, you cannot do your business of calculating cooling heating load. So heat exchanger theory, you should know. Repeat this theory of heat exchange. This is heat exchanger and its theory. How to find thermal resistance or overall heat transfer coefficient of heat exchanger. And there are two methods, LMTD method and electrical circuit method. These two methods are shown here. So you should know how to calculate thermal resistance or total of a cylindrical surface, of a flat surface. Everything is mentioned here. So heat and mass transfer from human body. This is the theory. This is the theory. These are the formula. You must repeat this. So for your convenience, I have copied them here, and you must continue to study them. Keep them printed with you for calculation of problems. Now, in this table, you can see this is also required for calculations. And I just zoom it for you. So this is design temperature data, but unfortunately this is for American cities, big cities. Like this, you will find Pakistani data also, and it is available on internet. It is available on ASHRAE handbook. It is available in other international handbooks. So you can find out Karachi, Pakistan, Islamabad, Lahore, these temperatures. These are design temperature. You know, this is for winter. You will take this outdoor temperature TO. For calculation of transfer unit TO. This is TO for winter. This is TO for summer. And this is design day average. So this is how we use this table. Now, there is another data table called required. So this data table is again given in your chapter 4 book, and these are materials mentioned, and they are 1 upon K. 1 upon K is the resistance, thermal resistance in the form of meter Kelvin per watt, meter Kelvin per watt, per unit length, and length is in meters. So now this is U factor, this is resistance R, reciprocal of U factor, meter square Kelvin per watt. So you may use this if thickness is mentioned here. Thickness is not. If it is not mentioned here, you take this and multiply with the actual thickness in meters, not millimeters. Thickness is usually given in problem in millimeters. You have to convert it into meters, divide by 1,000. Now these are different materials: sheathing, roofing, concrete, insulating materials. Here is insulating materials. So different materials are mentioned here and their resistance value. And this is for airspaces. Airspace may be different. Thermal resistance of airspace may be different situation, horizontal, vertical, or internal or external, or it is winter or summer. It depends on speed of the air outside. Now, flat glass, you are given directly U value. You are not given thermal resistance. You are directly given U value, watts per meter square Kelvin. And it also depends upon glass is single or double. And it's what is the thickness of the glass. Usually it's about 13 millimeter standard size. And for strong windows, their thick glass walls are used in the outer wall of the building, and they are 25 to 100 mm airspace between two walls in winter. This acts as an insulation in winter and summer. So you know summer and winter values of overall heat transfer coefficient. No need of calculating thermal resistance. U is given directly. This U separately will not add in thermal resistances. You have to calculate heat transfer through glass separately. You know, heat transfer through the glass has two parts. One, solar radiation, other transfer. So solar radiation is direct heat transfer inside the building by radiation. And that is given per square meter basis. That is a separate table. But there is a temperature difference between outside surface of the glass and inside surface of the glass. So heat transfer also takes place due to delta T, and that is used for that purpose. We use U. UA delta T is applicable for glass also. Glass heat transfer through glass is calculated twice. Once for radiation, thermal, solar radiation, and second transfer because of delta T. Delta T, temperature difference across the glass wall. So this was about properties. There's another table here. This shows table 2.1. This is chapter 2, and different materials are given. Thermal conductivity. If thermal conductivity is given in watts per meter Kelvin per unit length of the material, multiply the thickness of the material, you can get conductivity per degrees Kelvin. And here is convective transfer, boiling, condensing, heat transfer coefficients, and this is in watts per meter square Kelvin. So by conduction, you can calculate. By Fourier's law, you can calculate heat transfer from this property, thermal conductivity. Using Newton's law of cooling, Q is equal to Hc. This Hc, convective heat transfer coefficient, multiplied by area, multiplied by temperature difference between surface, heat transfer surface, and the free flowing film of fluid over it. Maybe fluid may be liquid, or fluid may be gas. So for convective heat transfer, use this Hc values, forced convection, free convection of water and air. So it depends on, see, water is boiling or not boiling. So you will need heat transfer calculation. This is typical construction structure of the wall. So these are again outside air space and sold example. So example 2.9 here, go through this example, do it by yourself, use this table, and you will become master of calculating Q is equal to UA delta T, heat transfer. Here you are required to calculate only R total, but here is Q. Q is equal to A delta T. Its units are watts per meter square, not watts per meter square. So UA, reciprocal of R total is UA, in Kelvin per watt. So in this way, that's why it's not watts per meter square per degree Kelvin. It is watts per meter square because R total contains U into A. U multiplied by A is already there. So this formula is actually Q is equal to UA delta T, where U is equal to reciprocal R total. This R total is different from that R total, reciprocal R thermal, because here A is also multiplied. So in this way, keep on doing. So my time is over, and inshallah we will continue tomorrow 9:40 one more lecture, and we will carry on further topics in this chapter, chapter 4 of your textbook. Okay, till then, peace. And we must end the meeting now.